Welcome fifth graders to the STEM Environmental Education Center, and a special welcome to the students at John Ireland Elementary, William M. Anderson Elementary, the Marcellus STEAM Academy, and the students at Anne Frank Elementary. Thank you so much for registering ahead of time for this field trip. If you are watching this and have not registered yet, you can still register for this field trip. You can do that by going to www.tiny.cc/EEC register to get yourself or your class registered for this field trip. We just use that information for attendance purposes. And today's field trip is going to be all about mixtures and solutions. So during this virtual field trip, students will observe that some mixtures maintain the physical properties of the ingredients and that changes can occur in the physical properties of the ingredients of solutions. So we're going to start off today by comparing and contrasting different mixtures and solutions. Next, you're going to see how a magnet can be used to separate mixtures. Then we're going to explore even more mixtures. And last, we're going to explore solutions. While we do all of that, you can ask us questions, and we encourage you to ask questions. But since this is a virtual field trip, you can't raise your hand and be called on. Instead, you're going to go to a website, which is www.tiny.cc/EEC-question-answer. And you can ask us any questions you have about mixtures and solutions, and ask as many questions as you like, and we will do our best to answer all of them in the time that we have with you this morning. So without further ado, we're going to get started with that comparison of different mixtures and solutions with Ms. Ramirez.
Hello, my name is Ms. Ramirez, and in this segment, we're going to do a quick review of mixtures and solutions. So we're going to go ahead and start with mixture. A mixture is just two substances that are combined and they keep their identity. So it can be two or more substances, and when you combine them, they keep their specific identities. So the first type of mixture that we're going to look at today is a heterogeneous mixture. A heterogeneous mixture just means that it's a mixture that you can clearly make out the individual components. So let's look at an example of a heterogeneous mixture. This is a seed treat. We have lots of birds out here, and this is an example of something that we would put outside for them to eat on. You can clearly make out the individual seeds that make up this seed treat. And if I look on the package, I can tell that this seed treat is composed of peanuts, sunflower, and safflower seeds. And again, I can clearly make out those individual components. Another example of a heterogeneous mixture is the food mixture that we feed to our chickens. So you can clearly make out the individual seeds, the corn, the crushed corn, the pellets, the barley that make up this seed mixture that we feed to our animals. So I'm going to show you guys a quick little video of some of our other animals that we have at the Environmental Center and how they eat different types of mixtures. So I'm going to share my screen, and since y'all can't be here today, I went ahead and just took some video of some of our animals eating various mixtures. And while you're watching this video, be thinking about what are some mixtures that you guys eat. So this first video clip is of our farm cat eating a mixture of different flavored cat food. We have Stuart and Bella the rabbits eating a salad mixture. Again, you can clearly make out the individual components, the lettuce, the corn, the apples, the carrots. You might have even heard Pepper the chicken in the background. Pepper the chicken is eating her own little mixture of freeze-dried mealworms, those long brown worms that you see, food pellets, and then the white dots are grit. She's also eating fruits and veggies as well. Then we have our box turtles. They are also eating a salad mixture. You can make out the individual components. We have the okra, the lettuce, the carrots, the apples. There's even some wet cat food mixed in there somewhere. This is a blue-tongued skink. As you're observing this video, be thinking about, is that an example of a mixture? Why or why not? And then justify or explain your answer. While you're thinking about that question, this guy gets his name blue-tongued skink because he does have a blue tongue. And then my challenge question for you guys, how can I separate this mixture of paper clips, pebbles, sand, and bark? So think about the physical properties of those substances. How can I use those physical properties to my advantage to try and separate those items without plucking them one by one with my hand? Some science tools that you might use would be a magnet, a sieve, which is the filter that you see right next to it, and then a bucket of water. So describe the steps and the processes that you would use to help you separate that mixture that I just showed you guys. So I'm going to stop my screen share and we're going to go back to our presentation. So I used the word physical property earlier. Remember back to a couple of weeks ago when y'all were learning about physical properties. A physical property of a substance we can use to our advantage to help us separate a mixture. So examples of physical properties would be like an object's color, its size, its ability to attract to a magnet, its density, so whether it can sink or float, its melting point or boiling point. Those are all properties that we can use to help us separate different mixtures. So the mixtures that y'all just saw were all heterogeneous. We can make out the different parts. The next type of mixture that we're going to look at is called a homogeneous mixture. That means that when we look at these mixtures, they look uniform or the same throughout. We can't really make out the individual components. So an example of a homogeneous mixture is a solution. So a solution is just a special type of mixture, and it's a homogeneous mixture. So an example of a solution that we use out here would be our nectar concentrate that we use to help feed some of our hummingbirds that live out here. So the nectar concentrate, when I mix this thick syrup, when I mix it with water, I get this nice solution here. So a solution, one of the characteristics is it's transparent. So light can easily go through this. So this is a good solution that we use out here to help feed our hummingbirds. If the hummingbirds don't have flowers readily available to drink nectar from, we can substitute that with some of our nectar concentrate and put it inside a hummingbird feeder. Another solution that I love to drink is water and a water flavoring packet like Crystal Light. I just put my powder in with the water. I mix it, shake it up really good. The powder dissolves, and then I have a nice lemonade. So lemonade would be a good example of a solution. Then we also have something that's kind of in between a homogeneous mixture and a heterogeneous mixture. It's called a colloid. And it's a different type of mixture. In a colloid, a good example would be like this pet lac. We feed this milk substitute to a lot of the baby animals that we have. And all this is a mixture of pet lac. It's a powder form. We mix this powder with water, and then we get this. So some people might call this a colloid or a colloidal solution or a colloidal suspension. It's a little bit different than a true solution. So a true solution, you can see the difference in the opaqueness. This one is transparent. This one is opaque. So that's the difference between these two. So what we're going to do next, again, since y'all aren't able to come out here, I have another little video of some of our animal friends and how they depend on different solutions and different colloids that we feed them. So I'm going to share my screen one last time, and we're going to take a look at some of those animals and how they depend on solutions and colloids. This first set of pictures that you're going to see are of hummingbirds. We do have hummingbirds out here at the Environmental Center. I just didn't have any pictures. So these are hummingbirds from Costa Rica. You can see they're feeding off the nectar. They have that nice long beak and tongue to insert into the flowers to reach that nectar. These are some baby cottontails that were rescued from a tractor accident. They were also getting that pet lac. That colloid. I raised them until they were a little bit bigger so they would be safe when they were released. The one that's missing the tip of his ear, I named it Patches, and then the other one is Bunny Foo Foo. They were released out at a farm, and I hope they are living a nice, happy life now. We didn't want to keep them because they are wild rabbits. They are not domesticated. We also have our baby calves that were also fed that pet lac. And then my last thing I just want to go over with you guys, we talked about mixtures and we talked about solutions. So if you guys were to do and create a Venn diagram, what are 3 things you know about mixtures? What are 3 things you know about solutions? And what are 2 things that they have in common? And then if you were to walk around your house or at school, can you find examples of mixtures and solutions? So I'm going to stop sharing our screen, and then we're going to come back to our presentation to do a quick wrap-up before we switch over to questions. So for a quick review, we said that a mixture is just a combination of two or more substances that keep their individual identities. So for example, we said a salad, you can clearly make out those individual components of the salad. And a mixture can usually be separated pretty easily. You can use a magnet, you can use a filter, you can just pluck them out by size. So that's a mixture. Then we have a solution. A solution is a type of mixture. And the type of mixture a solution is a homogeneous mixture. We can have liquid solutions like our lemonade. We can have solid solutions like metal alloys. So sterling silver is a metal solution. It's silver and zinc combined together. They melt those metals. It liquefies, and then when it rehardens, it turns into that metal alloy. Brass and bronze are also examples of alloys or solid solutions. And then we can also have gaseous solutions. So the air that we're breathing is a mixture of oxygen, nitrogen, carbon dioxide, and other gases. And generally speaking, a solution is going to be a little bit harder to separate. You're not going to be able to separate it with your hands or using a filter or a magnet. It's usually going to have to involve some form of evaporation to help us separate those components of a solution. So that's just a quick overview of mixtures and solutions. I'm going to pass it back to Mr. Broughton, and he's going to answer any questions that y'all might have.
Thank you, Mr. Ramirez. And the question that came in was, what other animals drink a solution here at our center? And off the top of my head, I can think of one kind of an unusual example, but we did have a baby raccoon here 2 or 3 summers ago. It was abandoned in our barn, and we fed it that powdered milk and water solution so that it could get a little bit bigger before we released it into our post oak preserve. It was a little bit too small when we first found him to just turn loose, so we let him grow a little bit, and once he was old enough, we turned him loose in our forest. All right, now we're going to move on to separating mixtures with a magnet, and Mr. Monroe is going to lead us through that.
Okay, good morning, students. My name is Mr. Monroe, and my part of your virtual field trip today is to do an investigation using a very special tool called a magnet to separate a mixture. And using a magnet to separate a mixture, basically, a magnet is going to be attracted to a variety of different objects that have a certain makeup in their matter. And before we get started in that investigation, I want to go over how a magnet truly works. You know, there are some common magnets that we see around us most of the time. Some of you probably heard of a horseshoe magnet, a bar magnet, or maybe even a ring magnet. Now, all of these magnets have something in common. The ends of those magnets are the strongest areas of attraction. The pull is greater in those ends. And that's for a reason, because those ends of those magnets, take for example, this horseshoe magnet. That's one end, and it has an S. That S stands for the South Pole. The N on this end stands for the North Pole. And the same on a bar magnet. There's an S here, that's the South Pole. There's an N up here, that's the North Pole. And of course, on a ring magnet, one side is the South, the other side is the North. Now, when you put those two poles together, they don't attract each other. They repel each other. I want you guys to remember that, okay? Now, for that magnet to be used as a tool to separate objects of different matter, one thing we have to realize is that the strongest attraction that a magnet is going to have is going to be to an object that has a content of iron in the matter that makes up that object. Now, magnets, they occur in those common shapes. Magnets can also be found in our natural world in the form of rock formations. And those rock formations are referred to as a type of rock called magnetite. Now, magnetite can be found all over the world. Some say that the original discovery of the magnet came from a country called Turkey. But we have magnetite deposits that are pretty close to our state. There are deposits found in Arkansas and Louisiana. Okay? Now, that would be the natural form. There's also another form that is man-made, and that is called an electromagnet. And we're going to use that process in a little bit. But first of all, I want to show you that in a mixture, if we use a regular magnet, it's going to be attracted to those objects that have a little bit of iron in their makeup. So I'm going to scan this bar magnet over this petri dish that truly is a mixture of objects. I'm going to scan it over the rock. Not responding to the rock, is it? How about a staple? It did pick up the staple. How about a penny? It did not pick up the penny. How about a piece of the metal that we call lead? It did not pick up the lead. So there are certain items in this mixture that it's going to pick up. You know, the first experience that I had with knowing what magnets can really do is that where I grew up in a little bitty country town, and not very far from my house was this huge salvage yard, breaking yard, scrap yard, goes by a lot of different names. And there was all kinds of junk in this big field. And there were wrecked cars, and there were old refrigerators, everything that possibly could be made out of metal, you could probably find in that salvage yard. And one thing I noticed that in the middle of that salvage yard was this huge crane. I tried to draw a picture of one by remembering what that would look back in the day. And I would watch that crane on days that I had time to really look, see what was happening. I would watch that crane pull up, and on the boom, the long arm of that crane, there was a cable that had an object attached to it. And I watched that crane lower that object over this big pile of junk. All kinds of twisted metal, even some old wrecked automobiles, cars. And we know that automobiles and cars are made out of a lot of different metals, right? So I would watch that, and then the boom would raise up, the cable would raise up, and that object would pick up a lot of that metal scrap. Some of the scrap stayed on the ground. And I'm thinking, what in the world's going on? Well, it wasn't until later on I found out that that big, large object on the end of the cable was a huge magnet. And it wasn't like the bar magnets, the common magnets that we see today. It had a cable plus a kind of looked like a big electrical cable running to it. And it wasn't until later on I found out that that was a man-made magnet called an electromagnet. And that electromagnet was controlled by an electrical current flowing through it. I watched that crane move over to another pile of scrap metal, and then all of a sudden, over that particular pile, it dropped all that was attached to that electromagnet. It was that salvage yard or that scrap yard's way of separating different metals from a huge pile that was a mixture. So magnets can be used. The regular magnets can be used to separate a mixture of matter that maybe has some type of metal in it. And an electromagnet is a large-scale way to separate metals also. What I have done here, I have created a small electromagnet. And we know that iron has to be part of the makeup of the matter that a magnet is going to respond to or attract. Now, what I have here is a 6-volt battery. And that 6-volt battery has a positive and negative pole on it. And I've hooked this up, and just to test it out, I've got a petri dish that is full of iron filings, pure iron. And let's see what happens. Wow, it's scooping it up. You guys see that? It scooped it up. Now, if I break the circuit, the electrical flow, look what happens. It dropped it. So that's how they were using an electromagnet in that salvage yard back in the day. My next step that I'm going to do is scan this mixture that I showed you previously. I'm going to hook the connecting up, and we're going to see what we can collect out of this mixture. Oh, we got a nail. We got paper clips. Some more paper clips, so that tells me that there's iron in them. Let's try this penny. Oh, no response. How about a dime? No response. How about that steel ball bearing? It's trying. Whoa, it picked up both of them, and it also picked up a brad. Okay, so it does work. And we started separating materials or matter from this mixture. Now, I want to talk a little bit about this steel bearing, ball bearing. This is an alloy. And you heard Ms. Ramirez say that alloys basically are solutions. Well, it is a mixture. And we can't really separate it like we separated this mixture. What has happened here is that in the making of this ball bearing, different metals were melted together to take some of the properties that those metals had to make this have properties that were what the chemists were looking for. For example, this is a stainless steel ball bearing. So, to make stainless steel, you have to have a little bit of carbon, you have to have a little bit of nickel, and you have to have a little bit of chromium. And you mix it into the proportions that you want to actually see those properties enhance this particular metal, which we call steel. Take, for example, stainless steel would probably be made up of 74 parts of iron. Well, that's a big content of iron, isn't it? And that's why it was drawn to the magnet. And then 18 parts of chromium, which that gives it its shine. And then 8 parts of what we call nickel. Now, nickel will keep that stainless steel from rusting. Now, you know, magnets play a very big part in our lives, students. Not just to separate mixtures like we just did, or not just to be used in a salvage yard, but you know, they're used in electrical motors. They're used in something that you might you might carry with you if you're lost or going somewhere where you might feel like you're going to get lost. And that would be a compass. You know, our planet has a North Pole and a South Pole also, right? Well, if you were to get lost, you would use a compass to find your directions, right? Well, the magnetic north would be drawn to this compass's needle, which because the needle is magnetic, it would point to the magnetic north. For example, in this classroom, I know north from my lab is that direction. I've got a compass here, and I'm not going to let these other magnets influence it. But if I hold it here, guess what? The hand is pointing north. So they do work unless they're influenced by another magnet. So students, hopefully you've learned a little bit about how a magnet can be an important tool to separate some types of mixtures that involve different types of matter that probably don't have any iron in, okay, in their content. And you also heard me talk about the way that a magnet works. Hopefully I've been able to help you learn a little bit more about mixtures and solutions and how they can be separated. And if you have any questions, I'm now going to turn it back over to Mr. Broughton, and maybe he can answer those questions for you. All right, Mr. Broughton.
Thank you, Mr. Monroe. And the question that came in was, how can I make an electromagnet stronger? And if you remember what Mr. Monroe did, he used a battery, a wire, and a nail to build an electromagnet. So it's just those 3 items. how you might make that stronger, you'd have to start experimenting with different things. So maybe try different nails, or maybe use a bolt instead of a nail to see if that doesn't make your electromagnet stronger. Or if you wanted to investigate with the wire, you could use a thicker wire or a thinner wire, or maybe change the number of times you wrap that wire around the nail or bolt. Or if you wanted to experiment with the battery, you could use a 6-volt battery like Mr. Monroe used, or you could use a 9-volt battery, or there are D-cell batteries, C-cell batteries. You could try different batteries to see which one makes the most powerful electromagnet. It would be a good investigation to do at home or at school, and maybe something you could even do for a science fair. All right, we're going to continue on with different mixtures with Miss Nash.
Hello, welcome to my classroom. I'm Ms. Nash, and today we're going to be exploring some more mixtures and how to make them and how to separate them. So mixtures are all around us. We've got those salads that we made for our turtles and other animals. We've got salads we make at home. We've got my favorite trail mix here, okay, that has fruits and nuts and on my computer there, not good. So I can separate them out and pick out my favorite bits. I can use my eyes and my fingers to pick out my favorite. I can use my hands to pick, my fingers, my sensitive fingers, to pick out the tiny bones from this owl pellet. I can use my eyes also to make sure fur and bones, okay, from the owl. I can also use tools and the properties of the materials to separate things. If I have an aquarium and some bugs fly in and die, or things fall into my aquarium, I can take a net and I can skim that water, and I can come out with things that are floating. So some things will float, and we can use a tool to separate them out. If I'm going to make a nice soil mixture for my plants, I might use some sand in the mix to help it drain better. I've got a mixture here of some sand and gravel, but I don't want that wrap. I'm going to take it, pour it into my steel here, and shake it up. And then when I open it up, I've got, and the coarser part of this lid, I've got the big pebble. I go down another one, I've got a finer mesh, and I've got little pebbles. I don't want those deep. Down here, I've got the sand. So this is what I might want to put into my soil mixture to help it drain. So I can use that tool to separate. If I'm making my coffee, I can also use another kind of little tiny sieve or filter to filter out the coffee grounds from the coffee. Now, Mother Nature has made some mixtures also. If we have a big storm in the mountain, rain, 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 things start washing down the mountain. Rocks, pebbles, sand, dirt. It's all washing down the mountain. Okay. And then when the water stops, things begin to separate out of that mixture that was in that storm water. This tool, this is called a sedimentator, and it shows us how sediment forms. So sediment is just when things fall out of the water. And if I take one that's been sitting for a little while, you can see what's going to happen. In the bottom, I'm going to have those bigger pebbles. Above that, I'm going to have sand, and then silt, right, like mud. And then up here, I've got in the water that colloidal suspension, tiny little things that are so tiny that they're suspended. Okay. So what force pulled all this down? Our friend gravity, right? So the density of these different materials separated them out into different layers like that. And then over time, those layers can actually form sedimentary rock, so that the pebbles at the bottom form that conglomerate rock. You can see the pebbles in there, right? And we have our sand, our sandstone. It feels like sand. Then we got the mud that turned into shale. Okay. And then here in Texas, we have, since we were under the ocean, we have our limestone and tiny critters that settles out of the ocean world. Now, we sometimes need to separate out a mixture to have our dinner. So this is wheat. It was domesticated a couple thousand years ago when it's now the Middle East. Okay. And we use it to make flour, to make bread, cake, cookies, yummy, yummy. And when we harvest it, we take off the head like that. And then we have to thresh it. And so now we use big machines to do that. But in the old, 1,000 years ago, they used animal donkeys to walk around on it, children to stomp on it. I'm crushing mine in this bag here to thresh it. And then I've got a kind of a mixture, a big mess. Okay. I'll show you mine. Kind of a mess. And in here, what I want are these wheat berries. Okay. So I can separate each one out with my finger, but that kind of takes a lot too long. So what could I do? Well, I can throw them in some water, and the seeds, the wheat berries sink to the bottom, and the chaff, that other stuff, floats to the top. But that's not very good because my wheat's now all wet, and I don't want it to be all wet because that's going to mold and rot and be no good. So the great advantage of this is it'll last a long time. So we do what we call winnowing. Okay, so if you go outside with a big basket like that one, you throw it up in the air in a windy day and watch what happens. I'm going to blow. I'm going to be the wind. You see how the chaff is blowing away. Do it again. So that lighter stuff blows away, and I'm left, hopefully, with a handful of wheat that I can use to make my cake and my cookies. So separating out mixtures is important for us, and also something else you think of in your daily life. The recycling bin. So here's our recycling bin, and it's got, in Dallas, we can recycle paper, cardboard, plastic cans and bottles, and they need to be clean. So this is plastic that is numbers 1 to 7. They have a number on the bottom. Some kinds are really hard to recycle. Cardboard, and paper, all kinds, not tiny bits of paper. I don't want it tiny. That's about as small as they want it. And glass. Of course, glass is the best thing of all because it can be recycled indefinitely. That means I can recycle, if I found an old bottle from the Romans, I could recycle it. So this glass can recycle forever and ever. So glass is really a good thing to be recycled, important. We can also recycle metal. Okay, like Mr. Monroe showed you how sometimes we separate out. We can also recycle aluminum. It cannot be recycled, separated with the magnet, but it can be recycled. Also really important to recycle. All the aluminum cans should definitely be recycled. Everything needs to be rinsed out, okay, so there's no sugar in that can. And then think about how are they going to separate this out at the recycling plant? So it's important to make sure you put the right things in the recycling bin and that they're clean and that you don't put things like styrofoam that can't be recycled. So I walk by my neighbor's recycling bin, they got all that styrofoam packing in there, and I think to myself, oh no, not again. We need to learn, and we need to help our adults around us, teachers and other adults, remember to recycle and then what to recycle. So you can go on the City of Dallas website and they have a list of what you can recycle and what you can't. It's pretty easy. And then do a little bit of research and see how those things get recycled at the recycling plant. And then a fun thing to think about is what is your favorite edible mixture, meaning something you can eat. Okay. Would it be a salad, a fruit salad, maybe pizza topping, maybe salsa. So what's your favorite one? And then think about all the things that go in it and what you could add to put something else in that mixture to make it even better. So cooking, a lot of cooking is just all about making a good mixture of ingredients. So enjoy making a mixture and eating a mixture. And if you have any questions, Mr. Broughton would be glad to answer.
Thank you, Ms. Nash. The question that came in was, what would happen if I put the wrong things in the recycle bin, like styrofoam? And what it does is it makes it more expensive to recycle because someone is going to have to take that styrofoam or whatever, if you put something else that can't be recycled into your recycling bin, it's going to have to be separated. That costs extra money. And if too many people put the wrong things in the recycling bin, then it becomes too expensive for the city to recycle, and they might stop recycling. It can also be dangerous for the workers if you put the wrong things in there. One example is like bottle caps can't be recycled. They could fall off a conveyor belt that carries the recycling things and then fall into the wheels that turn that belt and break it. It could be dangerous for the workers if that happens. All right, now we're going to move on to solutions with Mrs. Fuller.
Good morning, boys and girls. We're going to be talking about solutions. Solutions are mixtures, two or more things mixed together, but they cannot be separated out easily. We have solutions all around us. Windex is a good example of that. One of the characteristics of solutions is they are transparent. The light, and you can see through it. So you can look through Windex, so that qualifies. Another characteristic of solutions, the liquid that does the dissolving is the solvent, and the solvent dissolves the things that are put in it. Those are solutes. Well, some of the solutes, the solvent in Windex is water. Some of the solutes put in there is ammonium and coloring and fragrance and things like that. But the difference is that they don't fall out. Gravity does not pull these to the bottom like the sedimentator you saw just a couple of minutes ago. If you'll look at this, it's all clear all the way through. The stuff that gets dissolved in the solvent is dissolved at the molecular level, extremely tiny, and it's homogeneous. It's the same from top to bottom and side to side, and it's thoroughly dispersed within the solvent. I'm going to show you another solvent you're familiar with. I'm going to turn it like this so the light doesn't reflect off of it. This is mouthwash. Now, I found this is an old bottle of mouthwash. I found it in the closet, and it expired in January of 2018. If you look at the bottom, there's no particle. There are no particles down there. Nothing has fallen out of it. It's primarily water, but like the Windex, it has flavoring, and it's got saccharin and all sorts of things like that, and then a whole bunch of chemicals. But none of that stuff has fallen out because it's in solution. It's the same from side to side and top to bottom. It is a homogeneous mix. Now, I've made some tea here. I'm going to dissolve a sugar cube. Can you see the sugar cube? I'm going to put that in there. I'm going to stir it up. One of the characteristics of solutions, you can't filter out the things that were dissolved in it. So if I could put this through a filter, here's a filter, and here's a glass. I'm going to put the filter in the glass. I'm going to pour the tea in there. If I could filter out that solute, that sugar, I wouldn't be able to taste it, correct? But guess what, boys and girls? We'll move this over here so it doesn't make a mess. I'm going to taste it. It's very sweet. So the sugar did not filter out. So anything that you filter won't get it out. So how do we remove the solutes from a solution? Well, there are two ways. One is distillation, which we do not have time to go over or to do today. And the other one is evaporation. Now, you're very familiar with evaporation. Well, when you perspire, the perspiration on your arm evaporates and it leaves you cool, right? So evaporation is very common. I'm going to show you, and we're going to make a solution. The water is the solvent. Water is the universal solvent. It dissolves or more things than any other solvent. And it's because of the polarity of the water molecule. Okay, we're going to put some baking soda in, but you're very familiar with baking soda. You've got it at your house. Use it in laundry. You use it in cooking. You use it to make your skin feel better. If you get a sunburn, you can make a solution of it and soak your feet in it if you have a really tiring day. But I'm just stirring this a couple of seconds, and guess what we're going to have? The baking soda, which actually is mined. It's from a type of formation called trona, and they crush it up and make the baking soda. Look, it's already transparent. You can't see, you can see all the way through it. Just looks like plain water, doesn't it? And if I were to put it through a filter, it wouldn't filter out. Just like the sugar didn't filter out of the tea, the baking soda wouldn't filter out of the water. Okay, let's do another one. This is water again. Water's the universal solvent. We're going to dissolve some salt in it. So here's what salt looks like in nature. It's called halite. It has cubic cleavage. It always breaks into a cube. It's very interesting. And this is the kind of salt that we're all familiar with, Morton salt, table salt. The Morton Company has 20 facilities across the United States. We have one right here in Texas in Grand Saline. And the one in Grand Saline is on top of a 250 million year old salt deposit. And it's the cleanest, the purest salt, and the largest salt dome in the United States. And what they do, they pump water down into the salt dome, and it dissolves the salt, and then they pump it out, and then they evaporate it. They put it in big pans and let it evaporate. Well, you can tell it's already becoming transparent, and I can't filter it out. I could put it in a pan in the yard and let the sun evaporate the water, and the salt would be at the bottom of the pan. Okay, let's talk about another group of people. Ms. Nash told you about the Romans, how the Romans had glass, and that glass is, you can recycle glass from now on. Well, the Romans were very smart people, and they colonized the British Isles, and they found a place where the seawater was very, very clean. And they started a process where they removed the salt from the seawater. It was in Maldon, and guess what? They're still doing it, not the Romans, the English. But Maldon salt is very interesting. It's different from the little cubes that you would see in the Morton salt. This salt is flaky. I'm going to bring it over here so you can see it. It's a real flaky kind of salt. And the little salt bits, the little salt crystals, are in the shape of pyramids instead of in cubes. Okay, I'm going to show you one more before we go, and that's this fossil salt. This is from Redmond, Utah, and about 114 million years ago, there was a sea called the Sundance Sea, and it evaporated, and it left behind this salt, which was protected by a bentonite layer. You can buy this at the grocery store. It's a little bit different from the Mortons and the Maldon. It's not pure white. It has minerals in it, so you can see those in there. And it was separated from the water, from the ocean water, by evaporation. Evaporation is very interesting. Solutions are fascinating. I hope you have a wonderful day. And Mr. Broughton will answer any questions you have. Thank you.
Thank you, Mrs. Fuller. We're going to do a quick recap of what we did today. So I'm going to share my screen with you here. There we go. So today we explored mixtures and solutions, and during this virtual field trip, you observed that some mixtures maintain the physical properties of their ingredients, and that changes can occur in the physical properties of the ingredients of solutions. So Ms. Ramirez showed us a variety of different mixtures and solutions to get us started. Then Mr. Monroe used a magnet and an electromagnet to separate mixtures. Then Miss Nash explored even more mixtures, and you just saw Mrs. Fuller explore solutions. Thank you so much for joining us this morning. We'd like to know what you think about only our second field trip for fifth graders this year, and you can let us know by going to www.tiny.cc/EEC feedback to give us feedback on how we did today. It's a pretty short form, takes about 1 minute to fill out, and we use your replies and comments to improve what we do here. So I'd like to wish you a great rest of your day, and we'll see you again in about 3 weeks.